All right, prop 2 says, if a straight line be cut at random, the rectangles contained by the whole and both of the segments are equal to the square on the whole. So if we have, in other words, if we have some line, AB, and we'll choose any point on the line, let's see, I'll put it maybe right over here. So make any cut you like on the line. And then the idea is that we can form, with this cut, we can form two different rectangles by crossing one of the segments of the line with the whole line. So in other words, we're going to do AB cross AC to make this little rectangle. And we're also going to cross the uncut line with the other segment. So AB cross CB. So it'll be sort of this rectangle. And then the claim, which the diagram makes it very obvious, the claim is that those two rectangles together will be equal to the square on AB. Okay, so first things first, we will construct the square AB, ADEB. Yeah, so first thing, let the square ADEB be described on AB. All right, so I'll do that first. Kind of got some guidelines here to hopefully make this a little bit faster. So just making a square with side length AB. That's all we're doing. A down here is DE. Okay, so I guess this is proof. Construct square ADEB from AB. I guess it's kind of implied that we're building it off of AB since it's a square. And that was prop 46 from book 1. That tells us how to do that. Yes, 46. Yeah. Okay, and then the next thing that we do is we will draw a parallel through C. So a line through C parallel to AD or BE, whichever you like. It's the same thing. All right. So down here, this is F. We'll just say construct CF parallel to AD. In particular, such that F lies on DE. Okay. Yep. Then, of course, the larger square, AE, is equal to the sum of the two rectangles, AF and CE. All right. Yes, right. Oh, whoops. And then the parallel, I think I did this last time. I forgot to cite one of the pieces of construction. Making the parallel is prop 31. And those are the only two props that we actually need to use. Everything else kind of follows out. So let's see, what does he say now? AE is the square on AB. Yeah, of course. So I might say, what does he go on? He says, AF is the rectangle contained by BAAC, for it is contained by DAAC, and AD is equal to AB. And probably, let's see, what did he say? Yeah, AD is equal to AB. Right, we don't need to justify that because that's the definition of a square. All right, so what should I say? AF is contained by So AF is contained by AC, right? AC and AD is how I'll say it. So it's contained by AC and AD, but AD equals AB by construction. So AF is contained by AC and AB. I'm tempted to write something like AF equals AC cross AB, but I'm a little bit hesitant to do that right now, just in case, like later on, I haven't looked forward in the book, so I don't want to start using a notation now that maybe is going to muddy things up. I don't know. I guess we'll see in the next few propositions because that'll be a lot faster than having to write all of this out. Right. So yeah, AF is really just AB cross AC, and we're going to say the same thing of CE. Also, CE is contained by, maybe I can shorten it a little bit. CE is contained by CB and AB. Since, well, the quick way of kind of justifying that would just be to say that AB equals BE. I could also have used the fact that AB is, well, I guess I could have said it was CF is equal to AB, but I think that that relies on this anyways. So yeah, saying AB equals BE is maybe the faster way of that. So CE is contained by CB and AB, and really that's like, that's all that we needed to do. So maybe I'll say AE is equal to, and yeah, now that I think about it, I think I will use the cross notation. So AE is equal to AF, but AF is AB cross AC plus CE, which is AB cross CB. And that's what we needed to prove. Yeah, it's equal to the square. I guess maybe that's the very last thing that I should say. And AE is the square on AB. I felt like it was kind of obvious, but yeah, maybe I should just state that. Okay, QED. So there's that. Maybe the very last thing that I want to just kind of point out is that, once again, this is algebraic. So even though it's, you know, it's geometry, we're doing geometry, it's saying something about algebra. In particular, if we have some number x, it's like a real number, and maybe x is the sum of a and b, all that this is really saying is that x squared is equal to xa plus xb. That's algebraically what it's saying. And how do we kind of prove this identity right here? Well, it's not that bad just using some modern algebra. If we factor out x, then the right-hand side becomes x times a plus b, and we already have the identity right here that a plus b is x, so it becomes x times x, or x squared. That's a check mark. Check for like verification. Yeah, so that's really like what we just proved. This is the algebra of what we just proved. This is the geometry of it. So pretty cool. That's what I really like about this book so far, is that it's taking two different kind of branches of math that we normally think of as being different and distinct, and it's connecting them, tying them together. So super cool.